all of you. Welcome to the 15th lecture on the course on analysis and modeling in chemical engineering. In the previous lecture, we have discussed how do we represent a process by means of a flow sheet. What are the different approaches of solving the flow sheet problems? In today's lecture, I will take it one step further and try to demonstrate these ideas implemented on a commercial software, right? So, one of the things that I would like to emphasize here is the objective in this course is not to teach you a particular simulation software, and probably this is one of the last lectures where I am talking about any process simulation. We will, in the following weeks and the coming weeks, we will start talking about modeling in more detail of equipment like reactors, evaporators, before we come back of looking at how we can use graph theory to analyze interconnectivity, what kind of numerical solution schemes we have. So, we want to learn in this course the, I would say, the background of what really gets inside on the in the softwares rather than learning a particular softwares. Nonetheless, whenever you use a software, you will find use of whatever is being covered in this course, what concepts are being covered in this course, in like how it is kind of implemented, right? So, rather than using software as a black box, you can have a more informed design of the simulations that you are doing and more informed choice of like settings for those simulations, right? In any case, let me tell you like how, for example, things work in this popular software called ASPEN. The examples which I am showing you are taken from this particular book that is not too old, but it is already like 14 years old. So, ASPEN must be in a more recent version compared to what is being shown here, but the basic structure should be very similar to what I am showing. And if you use some other software, still you need to define different things. It may, the interface may look different, but the basic workflow will be very similar in any other software as well. Let's say HiSys or DWSim or whatnot, right? So, what do I have to do? So, first step is whenever you open any ASPEN or something, you will have kind of a blank window. The first step is to define what are the components in the system, right? And even before that, if you choose, you can already start drawing the units and streams, right? So, in the component specification, one is like we are saying that okay, these are the compounds which I will have in my simulations. But what is more important here is to have proper thermodynamic properties of those compounds under the conditions where they exist. So, I am showing you one example here of, let us say, N-butane, and this is the kind of window that is telling me the analysis of property of this pure component. And you see the kind of settings that we are doing here. We are looking at thermodynamic properties, probably what is present at equilibrium. We are looking at, let us say, the specific volume, the volume per unit mole. We are interested in the specific volume. The inverse of that is the density, by the way, in the vapor phase. That is very important because it will change if I change the phase. I want to specify also the temperature at which we want to compute it, because ultimately that is of our interest. But in this case, we are interested in kind of list of temperatures or a range of temperatures, right? And now if I do that, in this case I am doing it for a list of values. Basically, you can estimate how the volume is being calculated by the function of time. What is important here is the thing mentioned right here is the method that is being used, or the equation of state that is being used in order to compute this, right? As I was telling you earlier, this process simulations very often fail because the proper equation of state is not used for the component, right? Material balance and energy balance to a large extent is quite standard, and the softwares may not do any mistake with those calculations typically. But if you have given it a wrong equation of state which is not suitable for the compound in the particular phase they exist, in that case there is going to be a problem, right? So, of course, there is literature on what is more suitable for that. There are recommendations, but you must have some sort of a analysis to validate your model or simulation in order to see whether the properties are being done correctly. So this is for a pure component example, but the same thing can be done also for mixtures. Okay, so then the next step, or maybe earlier also you can do that, is to draw the units and streams, right? So I'm showing you an example of a compressor. Nowadays the softwares have very nice graphical user interface, so you can actually pick on like what equipment you want. So there is, as you can see, there is a list of things you can pick from. Whatever equipment you want to put, you just click it in there, it will appear, and it will come with some default streams, or you can also add additional streams as you require. And you see here in the list you have mixers, separators, heat exchangers, columns, reactors. So everything is there, right? So you have a whole library of different kinds of units that are there, and these are actually the kind of symbols that you have seen in the process flow diagrams. So essentially, by creating these things in ASPEN, you can actually form the process flow diagram. And this is an example of one of the process flow diagrams. So this is created basically by adding these units one by one, and then maybe connecting them in a particular way using these streams. And you see here that the streams are all labeled and the units are also all labeled, right? Essentially, we got a process flow diagram drawn, or if I have a process flow diagram, I can pretty much reproduce that using this, right? Now, whatever components I have defined, those components has to be defined for all the units where those components are going, and we need to ensure that whatever phase is relevant for that component in that equipment, that phase is specified in that equipment, right? Okay, next we have to go ahead and do the stream data, right? You see on the left here things are listed, what all things are required. So we require components, we require properties, and then we draw a flow sheet, and now we are at streams. And for the streams, of course, they will have some name, but more importantly, we have to specify its temperature, its pressure, and in this case, there are 4 components. So molar flow rate of all the 4 components. We can give inputs in multiple ways. The softwares have a large number of features. We can give in weight, we can give in moles, we can give in total, we can give in fractions, and all those kind of things are possible, right? So these are the specifications for the streams, right? In the example which I have shown in the last class, we made a table of the streams, but then every stream which they are connecting, now it is already drawn in the flow sheet. So when we draw it, that data is already present in ASPEN, right? So essentially, what ASPEN is doing is basically whatever I am drawing, it is using it to populate that table. But if I want to develop this software something similar to ASPEN, then I have to basically convert this flow sheet into a tabular information, and it was that tabular information which I was showing in the previous class. Or in fact, if I write, let's say, a Python code, and if I want to provide input regarding that flow sheet, one can give in tabular form, right? So on the behind of this, on the, I would say, on the back front of ASPEN software, essentially those tables, and those tables are converted into matrices and so on, are being operated, and the calculations are being done by that, right? So this flow sheet is only for the user to see and give inputs as required. Okay, so now similarly one can give the data for the units, and I am showing example again. Now we are at blocks, and for the blocks we have this, in this case, a unit, and for unit I am choosing it to be like a compressor. I can also choose a turbine for the same symbol maybe, and then they have a discharge pressure. Depending on the different equipments, you will have different conditions that you can specify for that particular unit. Going ahead, one can define the stoichiometry for particularly chemical reactors, right? Let us say you have the ammonia reaction, so it is N2 plus 3H2 to 2NH3. So nu here is specified as minus 0.5, then minus 1.5, and this side is 1, and you see it is in the stoichiometric order. So basically they are taking this ammonia as a basis. If I divide this by 2, I will get 1 by 2 N2 plus 3 by 2 H2 giving rise to NH3, and then this stoichiometric coefficient will make sense, right? And then I mean, I can also specify the conversion and things like that, although there are multiple ways the conversion can be calculated, right? But in this case, a fractional conversion is also specified for a particular component. So then one has to set up calculations, and there are models out there to do that. One of the common ways for doing reactor simulations is called R-Gibbs in ASPEN. What it does, it basically finds the thermodynamic chemical equilibrium conditions that is derived from thermodynamics. It does that, and it basically computes based on the Gibbs free energy and things like that. So provided that the reaction proceeds until chemical equilibrium, whatever is done by this particular model works well. There is another model that works purely on stoichiometry. One can specify the conversion and things of that sort, but this one is like based on the idea of Gibbs energies, right? And there are multiple tools out there which can do different kinds of calculations, right? And you see here again for the same units, now I am specifying the conditions, and you see here it is written to calculate the phase equilibrium and chemical equilibrium. So there may have been some change in phase in this case, maybe liquid to vapor, and also a chemical equilibrium. So this is a phase equilibrium with chemical reaction, right? Whatever I did in class for phase equilibrium, there was no chemical reaction. In this case, some chemical reaction is going on, right? And then we can have other settings depending on whatever calculations that one has to do, right? In this case, all components are being considered as products because it's based on the thermodynamic idea of Gibbs energy. We will try to minimize the Gibbs energy, and equilibrium constant is determined, or equilibrium behavior is determined using that, right? So therefore, that can be there for this particular block, but again it may change depending on the equipment that you have. So going ahead, if you simulate that, then if the simulation works well, you will get a list of all the parameters which are unknown for the system. On the back side of it, essentially for most of the process simulation code, they use a sequential modular kind of an approach. They perform some kind of iterations and they solve the problem and provide all the unknown data, which is my unit data and stream data, right? So of course, I need to ensure that the degree of freedom is equal to 0, but ASPEN or any software will complain if that is not the case, right? So therefore, you can solve it and you can get, in this case, for example, one can compute the molar flow rates of nitrogen, hydrogen, NH3 probably for the ammonia process, right? So you are finding those properties, and it can of course vary for this, right? So the key here is the unit data and stream data. And now, how are the units being modeled? The units are being modeled as whatever is physics for that system, right? So let us say you have a reactor. So we have to know reaction engineering thoroughly in order to model that. So that is being combined, they put there. Similarly, for the compressor, we do fluid mechanics. Similarly, for let us say a heat exchanger, you do heat transfer, and the connectivity is properly accounted for, that give rise to some kind of coupling between different equations, and that is also being done. So you have unit data, you have stream data, right? So at high level, this is what any process simulation software is doing. It is solving the units, it is solving the streams, and then it is doing it all together to get the answer that you want, right? All right. So I will take a simple example to demonstrate the comparison between the sequential modular approach and equation oriented approach. And the example I am taking is rather simple. So you have rather simple process, you have a feed, and the feed contains pure A, and A, some 1 mole per hour or something is taken as a basis, right? So there is a stream S1 for the feed, it goes to a mixer, and then the output of the mixer is a stream S2 that goes to the reactor, and there is some reaction given A to B in the reactor where 40% conversion is known per pass, right? What is per pass? And every time new reactant are coming, so all of them are getting converted into by 40%, right? And then finally, the output is my S3 that goes to a separator, and I am separating all the A. Separation, all the A gets separated. That means all the reactants are separated and they are being recycled by the stream S5, and then all the product B goes out in the stream S4, right? So let us say this is the problem, and I am interested in performing material balance for this particular problem, right? And let us say I want to do it by sequential modular approach, right? So what I will try to do, I will have to write first the equation of mixer. Let me label them 1, 2 and 3. So I will write the equation for the mixer, material balance equation. Then I will write for the reactor, and then I will do it for separator, right? Now, when I am writing the equation for the mixer, I do not know, I mean, I know that 100% A is going in the recycle. I do not know the amount of A that is going in the recycle, right? I know that it is 100% of A is going there, but how much is going, I do not know, right? So let us say that amount is some R, right? And now the question is, how will I find R, right? In the equation oriented approach, I will solve the equation for 1, 2 and 3 together, right? So R will be determined by the full solution, simultaneous solution. In this case, I will guess R, sequential modular case, I will guess and I will do the computation, and then I will, after the computation, I will get new value of R, right? So this is what I am kind of doing here, right? So we start from fresh feed S1, and in the beginning it is assumed that my R is 0, that is recycle is pretty much 0, right? So if recycle is 0, then how much A will go here? All the A that is entering from the feed will go to the reactor. Then how much is out of the reactor? 40% gets converted, so we will have 0.6 left there, right? Out of this 0.6, how much is the recycle that should have been there? Because all the A gets recycled. I am doing it for only the amount of A. So 1 A was here, 1 A is here, and 40% got converted. So we have 0.6 is the amount of A that is we have here. And since the A is not going here, all the A should have gone there. So R should have been 0.6, but we have guessed R as 0. So our guess is wrong. So now I will do second iteration, assuming that R is not 0.0, R is equal to 0.6. Now when R is equal to 0.6 and I have 1 here, instead of 1 here, now I will have 1.6 of A. And out of this 1.6, 40% get converted. What is remaining is something like 0.96 of A. And out of this 0.96, everything goes in recycle. So I got R equal to 0.96 here. That is still not the same as 0.6, but it is closer to 0.6 than the previous one. It was 0 and 0.6, and now it is 0.6 and 0.96. And I keep on doing the exercise until whatever value I obtain of R will be the same as the value which I guessed, right? You see here, second iteration, guess was 0.6 and we got 0.96. In the next iteration, we are going to start from 0.96 and I will get 1.176, and I will keep on doing it, and eventually you see the guessed value will become very, very close to the final value, right? And this is what is happening in the sequential modular approach, right? Now, at least for this flow sheet, you can say probably we didn't have to do it. If I put all the equations together, it would have been easier, right? And we will show that in the next slide. But in general, this iteration approach is, even though we are performing iteration, is not so much troublesome because the flow sheets are fairly complicated. Solving all the equations simultaneously sometimes is not so easy anyway, right? So even though we are doing iterations, it is not, I would say, so problematic because we are getting close to the final answer, right? So it looks like the answer is close to 1.5. and I am very fairly close to it in only 20 iterations. Right? Let us think about the equation oriented approach. And now you see, let us say if r would have come here, then 1 plus r should have gone here, and now 40% got converted. So what is remaining is 0.6 into 1 plus r, and this 0.6 into 1 plus r, now all of them gets here. And again I am doing it all for a, right? Now what should be this equal to? This r should be equal to this. How do I get it? I wrote the balances for all the units, right? So what does this give rise to? R is equal to 0.6 into 1 plus r. So this gives me 0.4 r is equal to 0.6, and this gives me r is equal to 1.5, which is the same answer which I got earlier. In fact, this is probably more accurate answer, right? Because we got in single step, no iterations required, right? How we got it? Because we wrote the equations for all the units and solved it together, right? At least for this examples, it may still appear to you that the sequential modular approach is probably meaningless, because why not do simply this approach for all the problems, right? But it is not the case. Simulation softwares typically prefer the previous approach because the flow sheets are fairly complicated, and solving all the equations together sometimes is not a choice, either computationally or otherwise. Okay. So, just to demonstrate that the recycle streams are what gave rise to this problem of iterations, let me now do the same case without recycles and see like how things will change, right? So, now if I am doing it using sequential modular approach, I will first solve for the mixer, and that will give me, if I have 1A here, I will have 1A there. So, now the mixer solution is done. And then I will do it for reactor. For reactor, I know that 40% gets converted, so it will become 0.6A. And then, I mean, in this case, since we are not recycling, right? So whatever A that I have probably goes out from the other part of the separator, right? So in this case, no guess was needed. In the previous case, guess was needed because there was a recycle stream coming here. If there is no recycle, there is no need for the guess. Now, I can also again do it by the equation oriented approach and try to do the equation for all of them, but it is not any different from what we are doing here, right? So, the point is, it is the recycle stream which are problematic for us, because recycle streams will make the equations simultaneous, and whenever we have simultaneous equations, they are difficult to solve, right? And these are the ones which are going to require iterations in your case. So with that, I summarize this week's discussion on process representation. We started from continuation of the idea of phase equilibrium from the second week. We discussed the Gibbs phase rule for intensive variables for a multi-phase, multi-component system. Then we demonstrated the idea and use of the degree of freedom analysis. We said what need to happen in order for a system to be solvable, that is, degree of freedom must go to 0. And then we looked at different kinds of process representations, the block flow diagrams, PFD, the process flow diagram, and P&ID, and we outlined the steps that goes into process design, which are synthesis, analysis, and optimization. And finally, we looked at how do we perform a process simulation. In order to do that, we need to basically have some kind of a representation of the units and streams in the tabular way that can go into the software, and we can solve those equations either by doing a sequential modular approach or by doing a equation oriented approach. And then finally, in today's lecture, we looked at how these things are actually implemented in the simulation softwares. I took example of ASPEN, but the similar ideas are also there in other simulation softwares, and in fact you can also build one based on these kind of ideas. So with that, I want to conclude this week's discussion on in this course. In the next week, I will start talking about modeling and simulations of chemical reactors. So with that, I stop here. Thank you so much.